Final example, if we've got a voltage of 120 volts and we put it over a light bulb, and that light bulb takes 100 watts of power, which is the standard incandescent light bulb, what resistance must the light bulb have? All right, so voltage equals current times resistance. But we don't want voltage equals current times resistance. What we want to know is power, right? What is power? Well, power was equal to current times voltage, which is equal to current squared times resistance, which is equal to the voltage squared over the resistance. So which one of these would be the best choice to pick? Well, we know the voltage, we want to know the resistance, we know the power. So this is the best one to choose. So power equals V squared divided by resistance. We plug in the numbers we know. 100 watts is equal to 120 squared divided by a resistance of unknown. So the resistance winds up equaling 144 ohms. All right, great. So 144 ohms. So compare that. 144 ohms is a fairly normal object, right? A light bulb. That's resistance in a light bulb compared to what we've got when we're dealing with that extension cord that we were just talking about. The extension cord has practically no resistance for what it's doing. So there's very, very little resistance compared to everything else that electric cord is going to wind up interacting with. So the current is going to not wind up noticing its resistance. It's going to notice resistance of what it's going to. So for its purpose, for our purposes, we will be able to treat that electric current as if it's all one equipotential surface, as if it all has no voltage drop over that wire. All right, so the other half of this, if electricity costs 20 cents per kilowatt hour, a reasonable price for electricity, a little high in some places, a little less than what it is in other places, how much would it cost to run that light bulb for 10 hours a day over the course of a month? So if it's 20 cents per kilowatt hour, and it's a 100-watt bulb, then 100 watt for 1 hour, well, how much energy was that wind up giving us? Remember, watt is power, so we have to multiply it by some amount of time to turn that into an amount of energy. And they sell us energy from the energy company, not power. They give us power through the lines, but we're going to buy energy. So 100 watts for 1 hour, well, that's going to wind up being 100 watt hours, right? If we're going to have that run for 10 hours in a day, then that's going to wind up converting to 100 times 10, 1,000, or 1 kilowatt hour. Okay, so we've got 1 kilowatt hour per day. If we run that for 30 days, then we've got 30 kilowatt hours. And then if we've got 30 kilowatt hours used over the course of our month of 30 days, reasonable length for a month, then how much would it cost? Well, 30 kilowatt hours times 20 cents per kilowatt hour, we wind up getting it costs $6. So, running a 100-watt light bulb for the entire course of the night is a nice convenient thing. It might be useful to have a hall light on at all times, but that costs you $6 to have that convenience. Something to think about. All of the lights you've got on, if you leave a light on all day, that's costing real money, and there's actually some reasonable things. It doesn't turn up that much, but over the course of a month or a year, it totals up to something you could really care about. So it's a good reason to keep your lights off when you aren't using them. All right, hope that was interesting. Hope you learned a lot, and we're ready to hit electric circuits where we'll really get the chance to start understanding something about how technology is working. All right, see you at Educator.com later. Bye.